Hi, stats students. Welcome back for section 7.3. Hopefully your confidence intervals are going well using our z-table and our t-table for small sample sizes or sigma unknown. Now we're moving on to section 7.3, confidence intervals. However, this time we're going to have proportions. So confidence intervals and sample size for proportions. So a recent USA Today snapshot stated that the percentage of respondents who have walked into someone while texting is 36%. Personally, I think that's quite low because I see some of you walk around with your phones and you're always bumping into things. So here's what that tells us. That one statement, 36% is a proportion or a population parameter. That is P, right? Probability of success. The sample size was 738 people. That's who's responded. By the way, that's like a convenience study, probably not the best survey to use because that's people who responded. And the proportion represents the part of the whole group and can be expressed as a fraction, a decimal, or a percentage, or represent a probability. So we could say something like P is equal to 0.36, or if we wanted to be technical, we should simplify that, 36 out of 100, or however you wanted to do that. So that's what our p-value is. So we've done proportions before. We've used these p, probability of success. Now we're going to use them to construct confidence intervals. So we got a lot of new notation or symbols. New but not new, right? We know p as probability of success. Well, it's still the same, but we're also going to say that's our population proportion. That's our population probability of success. Success in this case is walking into someone or something. P hat is new. It's hard to see it on here, but it's P with a little hat. That's why we call it P hat. P hat is the sample proportion. So plain old P is the population, P hat is the sample proportion. So P hat, technically, if I don't give it to you, is X over N. Q hat, I have two things up here. I really don't love the first one. Q hat, we could technically say is N minus X over N. I think it's more important to know that Q hat and P hat add up to 1. So if you know P hat, subtract it from 1. If you know Q hat, subtract it from 1. I'll just make a little note over here. P hat plus Q hat equals 1. So anything with a hat is a sample. We already know that P plus Q equals 1 as well, right? So we're just taking that into our sample. X that would be in that problem in the X over N for finding P hat is just the number of sample units that have that characteristic, the number of people who walked into someone, and then N is the sample size, just like we always do. So sometimes I'm going to give you P hat. Sometimes I'm going to ask you to calculate P hat. So let's look at one of each of those just so that you can see what that looks like. So example 7.7, find the sample proportion and its complement. Sample proportion is P hat. The complement, the other side of it, remember, is Q hat. So if N equals 80, our sample size is 80, and 45 people is X. I always think people, but 45 people have the characteristic that we're looking for. Find P hat and Q hat. So it's not given to us, right? So P hat is going to be equal to, maybe I did a sample in school and 45 people walked into someone while texting out of the 80 people that I asked. So I do 45 over 80 to find, oops, I forgot to put my hat. 45 out of 80 would be my P hat. I'm going to turn that into a decimal. I got a 5625. Since it was rational, I just kept it rational. So P hat is the complement. We could say, well, if 45 people out of the 80 walked into someone, how many didn't walk into someone? 35 out of 80, right? We subtracted. I just like to do Q hat is equal to 1 minus P hat. That seems easier to me. So 1 minus 0.52 or 5625 So Q hat's going to be equal to something like 4375. 4375. P hat and Q hat have to add up to 1. Now, in the second one, in B, for 39%, find P hat and Q hat, it's given to you. This is P easy peasy, right? So P hat is equal to 39%, just like those problems that we did in chapter 6. I give you the probability of success. It's just sample success. So then Q hat has to be equal to, it's the complement, adds up to 1, so 1 minus 0.39. So that's going to give us something like a 0.61. I really should put a 0 in front of those. So just, you have to look at the problem and figure out, are they already giving me P hat, or do I have to figure out P hat? All right, so let's do an example. Or another finding. So now putting all those P hats and Q hats into words, because right, that's really what we do in statistics, is we have a situation. 200 people were surveyed on if they were satisfied with their current job. 162 said they were satisfied. They like going to work. Find P hat and Q hat. P hat is the proportion of people satisfied with their current job. So P hat is the number of people, or the proportion of people. So 162 said they are satisfied with their job. Out of how many people did we sample? 200. So that's going to become something like a 0.81. Divide it out, make sure I did it right. So Q hat, we could be technical. You want to be technical about this? If we're going to be technical, it's the rest of the people. So 200 minus 162, that's how many people were not satisfied with their job. That would be something like, 38? Or I could just say 1 minus the 0.81 and get 19%, or 0.19 is the proportion of people who are not satisfied with their job. So that's where our P hat and Q hat come from. By the way, this was that little formula I gave you, X over N, that was in that list of terminology and symbols. All right, lots of symbols, right? We got new ones today with P hat and Q hat. We got these. The hats go with samples. The plain P's and Q's go with populations. So let's talk about making a confidence interval then. If we've got a proportion, we need to know what P hat and Q hat are. And we're going to make a confidence interval just like we always do. So here's our formula for margin of error. E is equal to, this is what we're going to add and subtract in our formula. We're going back to Z values. So E is equal to our Z value of alpha over 2. So again, we're going to go to our Z table. We're going to jump in and find what the Z value is. And we're going to multiply that by a really lovely looking square root of P hat times Q hat all over N. So that's a good one. You'll get used to it. Again, sometimes the calculations are harder than putting everything into the formula. We do need to make sure that N times P hat is greater than or equal to 5 and N times Q hat is greater than or equal to 5. Basically, I don't know if you remember section 6.4, but we are really just checking to see if this is a normal distribution. You don't even have to do that check step. I'll do them first and make sure that they are. But that does have to be true. Depends on how big our sample size is and how big our P hats are. And for these problems, we are going to round to 3 decimal places. Just make it standard. Now, if it comes out to something less, great, but typically because there's that square root, we're going to have irrational numbers. All right, so now the big formula, our formula for our confidence interval for a proportion, looks like this whopper. So we're not looking for mu, right? We're looking for our population proportion, so we're actually looking for P. That's why P is in the center of this instead of mu, which we've done for every other section. So we're saying, oh, well, the true population proportion of people who have walked into things is somewhere between these two values. So we do our p hat plus and minus our margin of error. So here's our margin of error, add. Here's our margin of error, subtract. I don't know if I've written it this way before, but I could say that p hat minus e and p hat plus e, if you like that as well. Margin of error is just what we wrote on that last page. That's what we're adding and subtracting. So our population proportion is somewhere in between these two values. Now, when we actually go to the population and find this out, it might end up being there, it might not, but we feel 98% confident that it will be in that interval. So let's construct a confidence interval. A sample of 500 nursing applicants included 75 from men. Find the 90% confidence level of the true proportion of men who applied to the nursing program. So over here on the side, I'm going to jot down a few things that I'm going to need to know. 90% confidence. So I need to know N, sample size. What is our sample size? 500. That's typically the easiest question to answer. I'm going to need to know my p hat. So p hat is equal to what? 75 out of 500. So 75 out of 500, let's turn that into a decimal. I believe that's 0.15. So 15% of the applicants is really what that's saying, right? It makes sense. In this particular set of applications, 15% were men. So that means what percent were not men? Well, p hat and q hat have to add up to 1 because that's all the applicants. So that would be like 85% or 0.85. And then my z value, we're going back to z. So it tells you to go to the z table, 90%. So remember, alpha then, 1 minus 90% would be 10% or 0.1. So alpha over 2, I should put alpha equals, alpha over 2 is going to be equal to 0.0500. So then I go into my z table, I find 0.500, I trace that out to find my z value. If it's in between, we're always going to go to the larger value. Hopefully I didn't mess you up with that, because we want more room for error, larger number. So I'm thinking that's a 1.65 for our z value. Now that we've got all that, now we can set this up. So I'm going to know that my p is in between two values. I start with my p hat, so 0.15 minus and plus that ridiculous looking square root. Inside that square root, I've got a fraction. It's p hat times q hat all over n. So 0.15 times 0.85 all over 500, square root at the very end, 0.15, 0.85, all divided by 500. Round to 3 decimal places. The reason we round to 3 decimal places is because, remember, we're finding the population proportion. So when I do the subtract side, the p hat minus the margin of error, I got a 0.124. So about 12.4% up to 17.6% is probably, with 90% confidence, I can say that that's for the whole population, that's the percentage of men who applied for nursing school. I can only base it on that. So we're going to go to 3 decimal places because we want to say, we can think to ourselves, oh, that's 12.4% at the lowest value. So these aren't different. They're just using different values, different calculations. Please check and make sure that you've got your calculation down, because like I keep saying, sometimes getting stuff in the calculator is harder than setting everything up. So there's one last thing we should talk about then, which is finding sample size. We did that back early in the chapter. I can't remember what section it was, somewhere in 7.1, I think. We are finding sample size, or N. So to find the sample size needed to determine that 90% confidence level, or whatever it might be, we solve the margin of error formula for the sample size N. I did it for you this time, and it comes out to N equals P hat times Q hat multiplied by your Z value, your critical value, over E, but you square that answer before you multiply by P hat times Q hat. And don't forget, we always round up for our sample size. No matter what, always round up. And I should jot this down as well. Do you remember that your key word for margin of error is the word within? I want to be within 2%, right? So we'd use 0.02 as our E. Because remember, this is all about proportions, population proportions. So it will be decimals, it'll be tiny little values for your E. So let's do one quick problem. I think we can handle this. So a recent study indicated that 29% of the 100 women over age 55 in this particular study were widows. Their spouse passed away. How large a sample is needed to be 95% confident that the estimate is within 0.03 of the true proportion of women over age 55 who are widows? Lots of words, right? But we caught a bunch of stuff. We need to know P hat and Q hat. We know that we need to know our margin of error to use that formula because it says how large a sample is needed. So we know we're solving for N. And we know that we're also going to need our Z, our alpha, or Z of alpha over 2. So P hat's given to us, correct? It's 29% of the 100 women. So 0.29, 0.29. We know, and we don't use that 100 women. It was just that. We want to know how many we need to do if we want to be 95% confident. So if P hat is 0.29, everybody knows what Q hat is, right? 0.71, those two guys add up to 1. Our margin of error, I see my red flag word here, within 0.03 or within 3%, I might type up. So 0.03. And 95% confidence level for my Z value, my critical value. So alpha is equal to 5% or 0.05. So alpha over 2 is equal to a 0.0250. I go into my Z table, and I believe that my Z value will be a 1.96. So now we just need to set everything up. N is equal to P hat times Q hat, so 0.29 times 0.71. And then I'm going to multiply that by my Z value over E squared. So Z value is 1.96 over my margin of error. Square that. I actually, when I do the calculator work, I usually do the 1.96 divided by 0.03. I square that answer, and then I multiply from there. I ended up with an 878 point something, 878 point like 9 something, blah, 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 blah. Always round up, so my sample size needs to be 879 people in order to be 95% confident that that's a good estimate. So I'm verifying, finding out, making sure 29% is a good estimate. That is it for section 7.3. Hopefully this doesn't feel all that strange. When we do confidence intervals, it all starts to be the same. It's just a matter of knowing, what do you need to know? Do you need to know P hats? Do you need to know T values? Where are you finding these things? So that is it for section 7.3. Thanks for hanging in there, and I will see you next time.